you, David. It's being recorded. That's great.
Okay, Mike, welcome.
All right. Thank you. Thank you so much, David, for inviting me. And I want to say this is joint work with Roberto Hernandez Palomares, who's like my collaborator on this. And I want to kind of put in a plug for Roberto. This upcoming year, he will be finishing his PhD, and he'll be on the postdoc market. And anybody who is able should take a serious look at him. In any case, I want to kind of tell a story about this program of kind of representing a rigid C-star tensor category over a C-star algebra. And I'm not going to claim that this is the first work of its kind. This is certainly not. But I wanted to maybe talk about what our work sort of brings to the table. So there's many types of reconstruction theorems in operator algebras. In operator algebras. And sort of one of the first ones was back to Popa, where he took a lambda lattice, which is a way to axiomatize a standard invariant of a 2-1 factor, and he created a 2-1 subfactor that realized it. And then a bit later, Popa and Schlatenko were able to take, again, a lambda lattice and always get a subfactor of LF infinity. And then after the formalism of planar algebras was developed, Guione, Jones, and Schlatenko did a diagrammatic reconstruction. So they did planar algebras. And they got subfactors. And this construction was purely diagrammatic. And so these are all in the land of subfactors. And then, since many of this was done with subfactors, is hope that we could do this with rigid C-star tensor categories. So for rigid C-star tensor categories, we have some work by Yamagami, which took a rigid C-star tensor category. And you sort of got it as bimodules over some 2-1 factor. And then along with Arnaud Berthier and Dave Pennies, we used the GJS type construction to take a C-star tensor category and embed it into the bimodules of LF infinity. So there's some results here for von Neumann algebras, and there's been at least a couple of results in the literature on the level of C-star algebras, and I'm certainly not mentioning everything, but I have to give a couple of shout outs here. Evans, Di Evans, and I'm gonna totally butcher the last name, so I'll just spell it. they looked at representations of braided TLJ into the bimodules of some C-star algebra. And Yuan took an arbitrary rigid C-star tensor category and embedded it into the bimodules of some C-star algebra. And this is also what we're going to do here, but I do want to make a comment at least a little bit about Yuan's construction, is that this C-star algebra is very much not separable. Even when the category is sort of countably generated. So it has countably infinitely many symbols. And it basically, it's an inductive limit of direct sums of B of H's, and the dimension of the Hilbert space is infinite dimensional. So that's very much a non-separable type thing. And so today, in joint work with Roberto, we're going to we take a C-star tensor category, rigid C-star tensor category, and we embed it into bimodules of, again, of some C-star algebra B. But B has some nice features. B is going to be separable. Be exact. It's going to be simple. It's going to have unique trace. And perhaps very, very nicely, the K theory of this B is very nicely described. And so the K naught group of this B is very simply the free abelian group on isomorphism classes of the simple objects of our category. And so we're going to have very nice pictures for what these bimodules are relative to this type of group. Okay, yeah, I realized, sorry, that was probably a pretty long history there. And I most certainly probably left somebody out. A lot of people have worked on this kind of thing. Any questions or comments so far?
Yeah, I've got a quick question. So in this result at the end here, the K note,
Yes.
Is that as rings or? The right-hand side is the fusion ring, right?
Yes, so I'm going to show you, yeah, there is a way to put, once I draw what the modules are, there's a very clear tensor product, and under that tensor product, you will get the fusion ring, and it's going to be the same fusion ring as in the category. Yeah, this has the same, fusion ring is the same ring structure.
There's a question from Alex. Are the bimodules correspondences?
So go ahead.
There's a question from Alex Kumjan.
Yes.
Are the bimodules correspondences?
Right. So B is separable. So yes, they are. I'm going to write them down explicitly in this talk. So yes, they are. They are in fact. They're going to be finitely generated projective C-star Hilbert bimodules. They're going to have two inner products and that play nicely with each other.
Yeah. Okay.
Yep. Right. Thank you.
K1 of B as well?
Come again?
Do you know K1 as well, B?
Oh yeah, actually we do. Sorry, I didn't mention it. It's actually extremely boring. It's trivial. There is no K. There is no K1. Okay. Any other questions? Okay, cool. Thank you guys for the questions. I like that. All right. So, all right. What are we going to do? I'm going to briefly talk about rigid C-star tensor categories. Now, there's way too many axioms for me to fully define them in this talk, but I'll at least kind of go over the graphical calculus and say some things that are important. So, rigid C-star tensor categories. All right, so it's sort of well known that we have this graphical calculus. So, i.e., if I look at the Hom space, so say C is the category. And then what I'm going to do is I'm going to write C of A to B, to just be the morphism spaces, from A to B. And part of the data is that this is a finite dimensional Banach space. And in fact, when the morphism is from A to A, it's even better. It's a C-star algebra. There's a dagger structure, which I'll talk about. But anyhow, for some F here, we can sort of represent it diagrammatically as follows. So you sort of have a string here with flavor A, say a string here with flavor B. So diagrammatically, we kind of represent things like this. And so, so with F as above, and say if G is in some C of B to C, then we represent G compose F, right, because that makes sense, as this type of diagram. And so it's sort of an A string here, a B string here, and heck, I'm having so much fun with the colors, maybe some sort of C string here. Okay, so composition is by sort of vertical stacking. You have adjoints, which correspond nicely with reflection. So you have with F as above some F dagger, which will be a morphism from B to A. Just sort of flip things upside down. And the rigid part, of course, is that objects have duals. So C has this dual. So C and C has a dual C check. And of course, with this, there come natural evaluation and co-evaluation maps. So you have evaluation and co-evaluation. So you have your evaluation C. So this is a morphism from a C check tensor C into the unit. And of course, diagrammatically, we represent it as this type of figure. So you have a cap. And then I'm putting a dotted line up to the identity, and we will soon not draw those types of lines. And of course, we also have a co-evaluation. The co-evaluation, which will be lying in the morphisms from 1 into C tensor C check. And it's going to look like a cap. So you have caps and cups. And they satisfy the zigzag relation, which is namely, it's called zigzag because you can draw the picture. So the identity on C check will be this. So of course, this is interpreted as the correct composition of evaluation and co-evaluation maps. And the identity on C will be the zigzag going in the other direction. So I should, be a little less lazy about labeling these. The C check, that's C, and that's C check. So you have the right combinations of evaluation and co-evaluation. So you can write these as compositions of identities and all these tensors and all sorts of other things. So objects have duals, and just one other kind of key piece of data is you have a dual functor. Well, so you have two types of things. So given F in C of AB, we have F dagger, which diagrammatically is going to look like this. Take an F and just twist the strings like that using the right compositions of these evaluations and co-evaluation maps. So this here is B check, this is B, this is A, and that's A check. And so of course this naturally lives in, so i.e. this F check is a morphism between B check and A check. So you have these dual maps, and you also have this map nu. You have this map nu AB, which is going to live in, to be a morphism from B check tensor A check into A tensor B check. And it's to be given by diagrammatically this. Which there'll be a correct interpretation for all this. Okay, so you have these are sort of well-known maps that are around. Yes, so just saying a couple more things. I'm sorry for the sort of quick overview. The idea is that neither of these maps a priori have to be unitary. There's no reason for this. But a fact is that there exists a canonical choice of duals to make both unitary. So it's called a balanced dual. So in fact, each object, each C and C, has a balanced dual, which we'll call C bar, and such that
The guy's still outside.
Sorry.
It doesn't work.
It's not working. And now it's
Oh,
Nope.
didn't plug it in all the way.
everything okay?
I'll make the hummus to go with your recipe.
Right. The balanced dual C bar such that this always holds. So such that this is going to be equal to this for all f in Hom C to C. And notice that when I write this, these are, because I'm not drawing strings to the identity, these are Homs from the trivial object to itself. And one of the axioms of the C-star tensor category is that we insist that that is a one-dimensional vector space. So it's a complex numbers, and so these are both scalars under this identification. Okay, and so we have a balanced dual, and the point is with the balanced dual, it turns out that this makes check and this new map unitary. We're going to assume that we have these balanced duals. So I'm sorry for this sort of rapid fire, just spewing diagrams at you, but hopefully you see at least a little bit of this diagrammatic calculus in play. So I'll see what questions the audience has at this point. All right, no news is good news. That's what I like to say. All right. Okay. So for us, let's kind of get into more the operator algebraic side of this talk. And so here's going to be one of the categories we're going to have that's going to play a central role. So we're going to let B be a, we're going to have more adjectives later, but for right now, we'll just say it's going to be a separable C-star algebra. I might not even need separable for what I'm going to write, but a C-star algebra with, say, a unique trace. So we're going to describe the category BIM TRFGP. And Roberto and I, we feel good when we work with this, and I'll credit Roberto for the name here. He calls it the category of happy bimodules. So maybe I'll sneak that name in there. The category of so-called happy bimodules. So I have to kind of explain what all these are. So these are going to be a subcategory of the category of all Hilbert C-star bimodules. So our objects are going to be Hilbert C-star bimodules with a bunch of structure. X, so, and these are going to be bimodules over B. So of course, what do these things come equipped with? So these are equipped with sort of two B-valued sesquilinear forms. Where the first guy here is going to be linear on the left, linear on the right. And these are going to be B-valued positive definite. So we're going to have two such inner products. We're going to require, we want them to give equivalent norms. To require that they give equivalent norms. So not necessarily equal, but at least equivalent, and of course completion in both. Actually, I guess you really need completion in one if they're equivalent. But we still need a bit more structure in this category than just these. So I'll tell you a bit more about the objects. So we require this sort of bit about being finitely generated projective. So what does that mean? We want there to exist a right basis. I.e., this set UI, some set UI, such that for all C, C is itself equal to this type of sum of UI, and then times here we have a right action, since it's a BB bimodule. Here, this is a right action of UI C. And we also want a left basis. These VIs. And we're going to require here that C will be equal to this sum I equals 1 to n of C against VI acting on the left by VI. Okay, so we have two bases, and for those who've seen tensor bases, these are the C-star, the algebra analog, and this is a concept that goes back to Wanatani. Okay, and so we're going to kind of throw some more requirements on them. So once you have a basis, you have indices. You have your right index, which is you're just going to sum the left inner products of a right basis. So the UI is above is my right basis. And the left index. There's going to be sum from VI, summing of right inner products of the left basis. Turns out that these are independent of basis, and these are always elements. These lie in the center of B. And so for us, B is going to have trivial center, since it's going to be simple. So these for us, when we write down our guys, these are going to be scalars. One thing which we're going to assume is such bimodules are going to assume, and we can always assume that they're going to be normalized. So any such bimodule can be normalized. I.e. that the left index is the right index. Okay, so they're going to be normalized. All right. And the last bit, and this is going to come when we discuss this important Hilbertization functor, is this trace part is kind of referred to as compatibility with trace. So not all bimodules have to have this, of course. But what do I mean when I say this? Is that we're going to require the trace, the trace on B of eta C to be the trace on B of the left inner product of C eta. So it switches right and left inner products and switches the sides. And so this is a requirement we are going to insist upon having, which is going to be true for the bimodules that I write down. Okay, and as you guys have probably studied, sorry, is there a question? sorry, the steering things. So you guys have studied these before. There's notions of tensor product. This would be the usual bimodule tensor product. So you have a tensor product, sort of notion of a tensor product, which I could get more into if you guys ask, and we have duals. In fact, it's very simple here. Here, x dual, the dual for x is going to be identified with this, which is going to be the conjugate Hilbert bimodule, which sort of switches the left and right actions with the cos of an adjoint. Okay, maybe perhaps one comment I should say is that I mentioned evaluation and co-evaluation maps, and so I would be remiss if I didn't mention what at least those were here. So I have an evaluation map, which is going to go from x dual tensor x, then this relative bimodule tensor product, into B as a BB bimodule, and it's very simply just going to send C bar tensor eta into the right inner product, C eta, and we have a co-evaluation. So there's evaluation on X. We have a co-evaluation, which is going to send B, this is going the other way, and it's going to map B into B times the sum over a left basis, or sorry, a right basis, where the UI with the right basis is above. And one can check that this sum is also independent of basis. Okay, so sorry for maybe bulldozing through some of that. Any other questions or anything you guys would like me to maybe elaborate on a little bit more?
There were a couple of questions in chat, but I think they've
I'm sorry. My head is like down and I can't even see the chat. Okay, go ahead.
No, I think they've been answered.
Oh, okay. Sorry, it's the awkward thing with Zoom. I have to like stare down at this. I'm like in my own world sometimes.
Excuse me, could I ask a question about the norm? Typically in Hilbert modules, the norm of an element is the square root of the norm of the inner product.
Correct.
And these are bimodules. You'll have two inner products to choose from, presumably.
Correct.
But you're telling us that the norms aren't the same.
Correct.
And so, okay, and so what's the norm situation then?
So they're not. So you are right. So I have two different norms, and you are right that that's how you compute them. Is you take take norm of an element, take inner product with itself, and take the norm of the square root in the C-star algebra. But so I have two different norms. One of the requirements here in the category is that the two norms. So I have two different norms on this space X. I just need those two norms to be uniformly equivalent to each other.
Okay.
Right, and so it's going to be complete in both, but yeah, they're not going to give the same thing. And when I write down the example, it will be clear that they're not going to be the same.
Okay.
Yeah, we're not going to require them. If they're the same, you get one of these impermittivity bimodules. Or close to it for
you don't want an impermittivity bimodule.
Yeah, we don't want that. We don't want that. So we don't want them to be the same.
Okay. Thank you.
Yeah, thank you for your question. Especially like it when I can answer it.
I think Alex has his hand up.
Oh no, I think he just asked. I think.
Oh, he's finished. Okay.
I believe so.
Right, okay.
Okay, so the remaining bit, we're going to sort of do our construction, and it's modeled very closely. I mean, it's using slightly different language, but it's modeled very closely after Guione, Jojen, Slotenko. So the construction. Okay. So we're going to, for simplicity, we're going to take C to have at least a countable set of isomorphism classes of simples. Without this, the C-star algebra we're constructing is definitely not separable. We're going to do a further simplification, and I'll say verbally how we can get around it, but just for the purposes of the talk. Is we're going to assume that C is generated by, we're going to assume that C is generated by, is tensor generated by a symmetrically self-dual object X. Not every such category has this property, but the way we're going to think of this is X is going to have a strand type. And so I'm going to kind of do this construction having sort of one color of strand. And then if you're feeling more emboldened and want to consider the general case, well, the general case is countably generated. And so now you just sort of have different strand colors for your generators, and things will kind of work the same way. So you just draw more colors in the general case. But certainly for every finite, for every category with finitely many objects, every, fusion categories, you could just take your object X to be the sum of all the object symbols with, sum of all isomorphism classes. Okay, so the symmetric self-dualities is just, it's a technical condition just to ensure that we sort of have positivity lying around. And it's basically saying that when I write down evaluation maps, that I can sort of be lazy and not have to write X dual. That there's this simple map that will do this. So it makes evaluation easy to write in co-evaluation. Okay, so based off of this, here's going to be how we're going to construct this beast. We're going to have some sort of Fox space type construction. I mean, I won't go into the full details of it, but hopefully you'll see how some of the elements here. Okay, so the first order of business is given integers, say L, B, and R bigger than or equal to 0, we let V, L, B, R be the morphisms from X tensor itself B times into XL tensor X R times. And we're then going to we're going to set this algebra GR infinity to be the external direct sum of all of these things. And so, of course, as we're sort of using the graphical calculus, I would be remiss if I didn't tell you what elements here looked like. And so you would sort of visualize as the span of things of this form. Span of elements of the form X. We're going to go from B, and then L strings here and R strings here. And I'm going to put this dot right there. So the dot isn't anything intrinsic to the category, but the dot is just telling you which summand of this direct sum you're in. Since we're taking this external sum, you're going to see the same element in multiple kind of orthogonal complements. So that's what that dot is there to do, just to tell you where we are. And so we have here, of course, this comes equipped with a few things. It comes equipped with a star structure. And now, since we have to be careful about interpreting these things properly as various Hans. If I have an X as shown, I'm going to define X star to be this type of diagram. So here is an X dagger. And here is, of course, some sort of evaluation or co-evaluation map. So here is going to be, this is R strings here and L strings here. And there's where the dot would go. So it's sort of some fancy way to reflect the diagram. So that's the star structure we have here. And we have, this is kind of the result I'm going to, it takes a bit of work to show. I'll throw it under the rug and say some of the ideas though. So a fact, so there's also a multiplication. On GR infinity. And it's the so-called Walker product. And so I will sort of write it here. So if I want to take some element X, say it's got K strings here, got L strings here, and R strings here. I want to multiply it by some Y, which has, say, L prime strings here, R prime strings here, and say J strings here. Then this is going to be this following sum. We put an X and a tensor with this Y. I bring over the strings to match, provided that they can match. So it must be the case that R had to equal L prime. And we slowly bring strings here one at a time. So I'm going to sum over this parameter L. L is actually a bad letter. Let's sum over this parameter I. So I'll put an I here. And so I is going to go from 0, of course, to the minimum of K and J. So I have this operation. It's an associative operation, and the fact I'm going to say, and I promise I'll tell you where the norm comes from. So a fact is that GR infinity completes to a C-star algebra, B infinity, which we're going to call B infinity, under this product and star structure. Now, at this point, it seems like the norm is kind of completely coming out of left field. So let me at least motivate, how would you see the norm? Well, you have a subalgebra you have a subalgebra of GR infinity, which we're going to call GR0 infinity. And GR0 infinity is going to be this direct sum of all VL0R. So it's going to be the stuff with no strings along the bottom. So no strings on the bottom. So sort of elements are looking like this. This is an AF star algebra. So there is a unique C star norm we can put on this that's going to agree with the norm that we would see in our category. So this is AF, so it is a unique C star norm. So it's a unique C star norm. So at least I have this subalgebra with this norm. And so the construction of GR infinity is some sort of Fox-based construction of, some sort of amalgamated type free product construction over this AF C star algebra. And the norm of an element of, say, some x in a GR infinity, what you do is you sort of, you compute x star x, and then there's going to be a sum of a bunch of diagrams, and you take the summand that is in GR0 infinity and take its norm. And of course, square root it. This is how you would go about getting a norm on this. Of course, these options, really what I'm describing here is some, C star algebra valued inner product. That's really what this is. But that's how one could find this sort of elusive norm that's floating around. Okay, so that's the sort of big amplified guy. So that's not going to be the C star algebra we have, but it's at least some sort of big amplified version where every bimodule we want can possibly live. So this is a big generator for all. So questions so far? Oh, and David, sorry, I have until 9:30.
Yeah.
Sorry,
Yeah.
half past. Okay.
Yeah, sure. No problem.
Okay, I'm aware. I promise I'll get to the good stuff here. Okay. Right. So here's what our C star algebra is going to be. So we're going to set So I'm going to set P naught is going to be this sort of empty diagram that kind of lives in here. And so this is empty diagram. And so we set B naught is going to be defined to be P naught B infinity P naught. That's going to be our basic C star algebra. And more generally, you set Pn to be this type of element, sorry. Sorry about that. Oh no, where did I just go? Okay. So Pn to be this type of element, where it's n strings here, and by the algebraic structure I gave, this is a projection. And Bn is going to be Pn, B infinity, Pn. Okay, so we have all these sort of corners we're looking at, all these sort of finite corners. Okay, so let me say some facts about this. And this is going to be the key one we are going to use. this B infinity is simple. And in fact, a much more pleasing result is true. In relating B infinity to B naught, B infinity is nothing other than, it's isomorphic to B naught tensor the compacts on some infinite dimensional Hilbert space. Two, there's a tracial weight phi, which on diagrams, which mapping an element which looks like this to this element, delta L equals R, and delta K is 0 of this. So you sort of just cap off the top. So that's going to be a scalar. And with this tracial weight, the von Neumann algebra generated by B infinity with this tracial weight is going to be some interpolated free group factor, tensor B of H, for some t. And this was shown both by GJS for the finite depth case and then me for the infinite dimensional case. So this B naught is some interpolated free group factor. And so we have this, and phi descends to a unique trace on B naught. So it's the only trace you can have, even on level C-star algebras. And now finally, because of course there's been the questions about K-theory, there's a very aesthetically pleasing description of our bimodules of our K-theory. So K naught of B naught is nothing other than the Z-linear, the group, the free abelian group on the isomorphism classes of simples. And the way we see this is that simples here, each simple kind of gives rise to a minimal projection. So it corresponds to minimal projections. And they sort of look like this. P, some sort of projection P here in GR infinity. So kind of all the standard minimal projections in GR infinity, this AF subalgebra, those are the guys that are actually generating my K-theory. So it's really, really coming kind of directly from the category. So it's quite aesthetically pleasing. Okay. So that's what our K-theory is. I'm running low on time, so I'm just going to turn this sort of into an art project and talk about our main bimodule and kind of say what it's going to do. So what is our bimodule, our sort of main bimodule? Is our main bimodule. So we're going to take our x, we're going to define it to be some some corner of this B infinity. And so it's going to be, diagrammatically, right, it's going to look like elements of this form. So you have a single strand here, and then kind of how many things you want there. So all elements look like that. So you have an obvious left B naught action. Is by multiplication. And we have a right B naught action. which I will just sort of draw pictorially for when something is a diagram. Which, if I sort of take something here and I want to have some element x act on it with no strings on top, this is going to be defined as, so my right action is now going to be defined as this picture, this sum of C. It's x, where again, we just pull over things. So basically, yeah, you just pretend that the dot is sort of on the other side. And of course, there's something one has to check that this extends to a norm continuous action, which we, of course, we do. So there's a left and a right v-naught action. And now, because of this, I will just say what the inner products are and then just state our result. So our left inner product. So let me do the actually let me do the right inner product first. So our right inner product is going to simply be this type of picture. So if things are diagrams, if you pretend everything is a diagram, it is the continuous extension of this mapping. Sorry. Wait 1 second. Yes, I am right about that. As continuous operation of this mapping. And our left inner product is going to be this type of picture. So I just put the star on the other side. And with care, these can be realized as certain multiplications in some corners of this algebra. So this is going to be compatible with my trace phi. But these do give different norms, but we can check their equivalent. Okay. So now let me kind of state the theorem, and I know I'm giving it short shrift, but let me at least state the result, and then I can probably open the floor for questions after that. So the theorem is the assignment of X tensor n into this capital X tensor n, which is going to be a pictorial representation for that, induces a fully faithful bi-involutive functor from C into this category. So that's the key, is that we can kind of pictorially represent all these bimodules, and we can realize intertwiners by just stacking boxes on top. So, okay, I'm very sorry I went 2 minutes over. Why don't I stop now, and then I can elaborate more if people have questions.
Okay, so thanks very much for that talk. Right. Let me